about leakage current mechanisms in amorphous hydrogenated boron carbide with reference to DC conducting mechanisms. The question is, why are we doing this? Why is it important? Well, we have two primary applications in which we're working with this, which would include the interlayer dielectric and neutron direct conversion neutron detectors. In each of these, understanding the leakage current and dielectric constant and mobility are very important in optimizing these properties. Specifically, that of, for both cases, optimizing and understanding these field transport properties. And so the goal is to understand these and then relate it back to both of these applications. So why amorphous hydrogen boron carbide? Why is this important? Well, it's known for its high hardness, and that B10 has a large neutron cross-section, which makes it kind of important for both cases. It has strong intra- and intercosahedral bonds, and that's what gives it that chemical hardness and chemical stability. And also high activation energy just due to those high defects of this amorphous material. It has low Z components, which give it that nice K that we're kind of looking for. And so, and a low electronegativity differences. And so, and then due to the fact that we can grow it through PCVD, we can hydrogenate this and hopefully decrease gap states and other things, changing the conductivity. And that's one thing we want to look at. And so boron carbide kind of becomes very interesting for both applications in just its structure and its properties. So for DC conductivity and mechanisms, we have a metal to dielectric kind of device, MIM or MIS structure. And the idea here is that there are two types. There are injecting mechanisms and there are conducting mechanisms. You want to inject charge into the solid, and you also want to, so you have mechanisms in which you're injecting charge from the metal into the solid, and then you have mechanisms in which you're traveling through that solid, right? So you can have a percolation type thing, because it's amorphous solid. This is more physical based, almost like water running through drainage, or electronic, where you're doing hopping between states. Either way, you have different types of regimes where you have ohmic, Schottky barrier, where you have accumulation of charge here, where the dielectric is almost separating the positive and negative until there's an overload and you get space charge that are now being injected into the dielectric, and etc. And then you have different types of Poole, Frankel, and Fowler, and we'll talk about this. But the question is here is that what type of injection and conduction mechanisms does this solid have, and what does kind of and what is the main mechanism, and what does it imply for these trap and defect states? So various transport mechanisms being ohmic, and all these are field dependent. These are DC mechanisms, and so ohmic and space charge limiter are in the low field range, usually 0 to 20 volts, very low range. Whereas Frankel-Poole and Nornheimer tunneling, this is also Schottky tunneling, where you create a Schottky barrier. And this Frankel-Poole would be trap-assisted tunneling or multi-step tunneling. Each of these, and these are high fields. And so what we're going to do, what I do in this talk is I'm going to analyze each of these as a function of current density, as a function of field, and try to fit and see which one of these mechanisms apply for our material. For this study, we did just kind of a range of stoichiometries and densities from 2.4, which is very almost sputtered boron carbide, to 0.9, which is very low. So we did a range of, it was grown through PCVD with a single solid phase precursor orthocarbon. And so experimental, we looked at an MIS structure where you have aluminum to the silicon, the dielectric, and a mercury. So we use a mercury probe to get a J versus E or J versus V curve. And then UV-vis spectroscopy was used to extract band gap, Tauch slope parameter, where Tauch slope parameter is a measure of the overall topological disorder of a network, and Urbach energy, and this is potential fluctuations caused by strain in micro parts of the network. So it's just strain and weird bonds, whereas Tauch slope is more the total disorder of the network, and then band gap is a separation between the conduction and valence band. Was used, and then a Tauch slope was used to get the band gap. So here is a results of J versus E for various stoichiometries and various densities. We can look at, you can take just one of those curves. This is a very typical curve, and we can kind of look at different regimes in which we can see ohmic space charge limited and Poole-Frankel emission. as a function of bias. Looking closer, we do an analysis of ohmic, which is just related to, and then we do space charge limited, which is going to be e to the squared law, and we can see with just one of these that slope here is approximately 2, which is showing space charge limited, and this is showing ohmic. And then using that analysis we talked about, we can extract Poole-Frankel and various dielectric properties from that. So looking at all these curves, we get that the ohmic conduction, we see evidence of both ohmic and space charge limited current, where the ohmic conduction revolves around 0 to 10 for the majority of these films. And from the slope of the ohmic, we can extract resistivity, and there we get around 1 times 10 to the 11 to 10 to 15 ohm centimeters. And that power law, which here is the n for the power law of each of these, and remember it's n e to the squared is the one that shows space charge limited, so we see that each of these show evidence of space charge limited current, and ranging around 11 to 40 volts, and this can give information on charge mobility. However, the assumption is that it's very low defect, and due to the fact that we do have defects, the mobility we extracted from here, ranging from 10 to the minus 7 to 10 to the minus 2, which is a very, very low mobility film, but however, this will probably be reduced further with the defect density. And we also see evidence of Poole-Frankel, where Poole-Frankel, if you look at a typical bandless conduction band for an amorphous solid where you have a lot of defect states, this would be multi-step tunneling happening that would give this Poole-Frankel kind of conduction mechanism at these high fields. And one way to extract whether it's Poole-Frankel or whether it's Schottky at these high fields, which one's the leading mechanism, is that through being able to measure the dielectric, if through your analysis the Poole-Frankel is close to the dielectric constant, which I measured from ellipsometry, then Poole-Frankel is the leading one. However, if it's off by an order of magnitude higher or order of magnitude lower, then it's most likely Schottky barrier. That's the leading mechanism. So for these films that we have here, we see that Poole-Frankel is actually the leading conduction mechanism of these high regimes, just due to the fact that these dielectrics are close that we measured. And we also see that with lower leakage current, with these ones that have low leakage current, they in fact have higher y-intercept, and that y-intercept is actually related to the energy of the depth of the wells. So the more energy those wells are, the harder it is to extract a charge from that, and therefore lower leakage. So so we kind of, for a few correlations based on those UV-vis properties, we see that the y-intercept of the Poole-Frankel, which is related again to the energy depth of those wells, as a function of Urbach, that as we increase that Urbach energy, that strain or stress in the network, in fact, we're increasing that trap density. And if you look at the slope of the space charge limited, which is related to that mobility, as a function of, this is the tau slope parameter, and as this increases, the overall disorder increases. So most likely this is leading to more scattering as we're pushing these charges through the film, and in fact we see that the slope itself, so as the mobility is actually decreasing, or the slope itself is decreasing as we increase that total disorder. And then the relation between mobility and resistivity on measured films, an inverse relation, which is kind of what we expect. And so we kind of conclude that disorder and lattice strain play an essential role. And so, in summary, we know we can optimize the ohmic and space charge slopes through optimizing that disorder. For high field regimes, we know that Poole-Frankel is the leading mechanism. For better leakage current, so that's what we're kind of trying to optimize, right? We want high resistivity and low mobility in that low field range. And then in that higher field range, we have the Poole-Frankel mechanism taken over, which is multi-tunneling hopping through that gap, is that we want a higher energy gap, i.e. It takes more energy to get those films out. And then for film density, we see that for really high dense film or a really low dense film, the leakage current is really high and the breakdown. Leakage current is really high, the breakdown is really high, and we can kind of start to optimize that leakage current with having kind of like a middle film density. And so for future work, we want to look at larger set of parameter space, growing new different types of films, compare the mobility where you extracted to the space charge limited with that of photoconductivity methods. Also look at AC conductivity, and that way we can extract AC conductivity mechanism. Rawness spectroscopy to correlate with hydrocarbon bonding to that leakage current mechanism to kind of get a better idea of what hydrocarbons are doing to the leakage current. And then also defect analysis and electron spin for spin density. And again, we can relate that back to the Poole-Frankel conductivity. So that's it. What was the time?